This one, right?
Yes.
Copying it into this procedure. Do we copy the procedure verbatim from this?
You can. You don't have to. You can put it in your own words. You can put in details that you may have picked up reading elsewhere in there. What you want to do is have enough detail so that you can take your lab notebook and go do the experiment. And if you think you might need some information that's not actually in the step-by-step procedure, put it in there. Yeah. And then while you're doing the procedure, something may go wrong or change, and you may make an observation in there, so that when you write your report, you can actually say what did happen, not what's supposed to happen, but what did happen. So that's if you look at the rubric, you'll see that there's a section on grammar, and I'm especially keen on getting the grammar right, because the procedure is going to say, cookbook, do this, do this, do this, do this. When you write your report, you want to say what was done. So you would say something like 50 milliliter sample of ethanol was measured using whatever. So it's passive, third person, passive past tense. You don't ever say I, you don't ever say you. It's always in the third person. So here's the subject of the sentence: 50 milliliter sample was measured. Past tense, passive. Okay? That's what I'm looking for. And of course, if you check out the example, the sample report. In fact, I think one of the sample reports is Boyle's Law. So if you look at that one, you'll see almost exactly what I expect to see in your report. If this is the first one you've ever written, then that may help. Okay, so we're going to do a little review, and I got about 20 minutes before I have to break. I thought I had marked out some, I did pick out some just in the past few minutes that I definitely want to get to. But we're going to look at the review document and just run through a few things and see if there's anything that highlight that needs to be attacked for something later. I laid it down somewhere on there. Okay. This shouldn't be a difficult one. Gases generally have what? Low density? Yeah. Closely packed particles? Absolutely not. High density? No. No increase in volume when temperature is increased? That's ludicrous. No decrease in volume when pressure is increased. Okay, so really the only one that fits is low density. What's the definition of pressure? Remember that one? Pressure equals force per unit area. It's an intensive property. In other words, pressure stays the same no matter how big the area. You increase the area, you increase the force. Okay. But there are units associated with it. Let's see. Defined as the force per unit. Oh, well, okay. We got that answer all right. SI unit of pressure. You remember that one? I'm not showing you the answer down there yet. The Pascal, yes. And the Pascal has a definition associated with it too, that 1 Pascal is a Newton per square meter. Get one, find one that works. Okay. Now, if you have something like this, which one of the following is the greatest pressure? Right? You can't compare different units of measure. You got to go in and make a conversion to some common unit. And probably the best approach is to go to atmospheres. This one's easy to convert, 760 millimeters per atmosphere. 14.69 psi per atmosphere would convert that one. Pascals. That one you might have to look up. Right? At the back of your review document. So how many pascals in an atmosphere? It's like 101,000 something in it. Where is it? Here we go. Units. Here we go. 1 atmosphere equals 101,325 pascals. Right? So you just modify the units. And inches of mercury. Remember which one that is? Yeah, it's in here. 29.92 inches of mercury equals 1 atmosphere. So with those conversion factors, you can convert all of these to atmospheres and compare the values. And as it turns out, 11.4 psi has the greatest pressure of all those. Okay, let's see. Let's get past these easy ones and maybe get to one. Let's see. Oh, can you identify the gas laws? Right. What's the first one? Historically speaking, the first one was Boyle's, right? These are the gas laws. Boyle's was relationship with what? Pressure and volume equals a constant. Who's next? Charles. Charles' law says relationship of, that was about volume and temperature. That's equal to a constant. And what else can we see with these relationships? If two variables in a product situation, one times the other is equal to a constant, that's an inverse proportion, always. Because if this is constant, then if that one goes up, this one has to go down. This one is a direct relationship. If that one goes up, that one's got to go up to maintain the constant. What's the other one that we studied? Avogadro's law. And it's a relationship of volume and moles. That's also a constant. Okay. Now, are these useful? Not as they are, they're not useful. What we need is a relationship between initial conditions and final conditions. So if we set them up like that, then initial conditions are equal to final conditions, like that ratio. And this one, initial, final, final. So when you're using these formulas, it's probably a good practice to read the problem and extract from the problem conditions. First of all, identify whether it is a before and after situation. Right? In this case, if it's asking for the final volume, does it have two pressures and an initial volume? If it does, yeah, that's where you need to go. And then list, if you're going to use this law, list VI, TI, VF, TF, and put the values that are equal to them up there. Identify the values first. Before you try to plug them into the equation, you try to stick them in the equation straight out of the problem, you might get them in the wrong place. Now, one other caveat. Temperature has to be in Kelvin. If it's not in Kelvin, it will not work. Okay, so those are the individual laws. What else did we learn? The combined law, correct? So the combined law is fairly easy to deduce from that. Initial, 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 initial. And that's equal to final. And this again is for before and after conditions. So you can let all these things vary. As long as there's only one unknown, then you can solve for it. Or if you say this is your starting place, suppose the volume is held constant. If the volume is constant, then that term drops out. And all you need is the other variables. Or if moles is constant, that term drops out. Okay. All right. So we're not going to stop at these laws because we just got through talking. But how about, let's see. All right. We can spend time on these problems. I don't want to waste your time when we could be doing more interesting problems. These are very simple problems. Is this a before and after situation? Constant pressure. First, the gas occupies this volume, 3.62 liters, when the temperature is at that point. So immediately, your mind ought to drift toward Charles' law, volume and temperature. Determine the temperature at which the volume of gas is 3.42. Okay, so now you have two volumes and one temperature. So set it up so that you've got your VI, TI, VF, TF set up. You put those numbers in there and say, okay, now I know where the numbers are supposed to go. Solve the equation. How about, I wonder if this one might be good. You have 41.6 grams of oxygen in a container with twice the volume. You have 41.6 grams of oxygen in a container as twice the volume as one with CO2 gas. Okay, sometimes it helps to draw a picture. So this is the one with oxygen. And this is the one with CO2. And this volume, CO2, is equal to this one times 2. This one is twice the volume of that one. Pressure and temperature are the same. Okay, pressure, temperature, constant. What's the mass of carbon dioxide you have in this container? Right. We have 41.6 grams, right? Okay. How do you solve that problem? Avogadro's hypothesis is where I would go. Because Avogadro said, if the pressure and the temperature are the same, and the volumes are the same, then you have the same number of moles. But this volume is twice of that. So this one has twice the moles of that one. Correct? So how many moles do you have here? Well, you just need to divide it by 32. Right? The molar mass of oxygen. So that's the number of moles of this one. And then twice that would be the number of moles of this one. So that's equal to the number of moles of CO2. Okay? So once you find the number of moles of CO2, what's the mass of CO2? We need moles down here, correct? And grams up here. So what's the molar mass of carbon dioxide? Well, it's 32 plus 12.01, right? (44.01). There you go. So this tells you how many moles of oxygen. Actually, this tells you how many moles of oxygen. This tells you how many moles of carbon dioxide. And then you take that number, multiply it by this, and you get your answer. Okay? Is that a mystery? Or does it seem reasonable? Could you do that on your own? That's the question.
Answer is 28.6.
Yeah, 28.6, right. So if you do those calculations, you should come up with that number. All right. Now, if we've got temperature changes, and we're going to use Charles' law here, don't forget to change that to Kelvin. Because the ratio of these temperatures is not the same as the ratio of Kelvin. Let's see. This is a good logic problem. Suppose you have a sample of gas in a container, and the Celsius temperature doubles. So you have one temperature here, initial, and then the final temperature is double that one. But this is in degrees Celsius. Okay. You transfer the gas to a container with twice the volume of the first container. If the original pressure was 12 atmospheres, and the volume now over here is going to be twice this volume. So we would expect that if the temperature didn't change, what would happen to the volume? Twice the volume. What would happen to the pressure? If you went from this and you increased, you doubled the volume, then the pressure should be 6 atmospheres, right? That's without a temperature change. But what if the temperature doubles? If the temperature in Kelvin doubles, right, then the pressure would be back up at 12. If you double the temperature, then the pressure would go back up to 12. But we're doubling the Celsius, not the Kelvin. So if you're saying 273 plus TI, and you double this one to 273 plus 2 TI, what effect does that have on that ratio? Not much. It will increase the pressure back towards 12 from here, because you did increase the temperature a little bit, right? So a good estimate would be something greater than 6. It wouldn't be 12, definitely wouldn't be 15. Because it wouldn't be 12 because we didn't double the Kelvin, we doubled the Celsius. But it wouldn't decrease either. So this one is probably the best estimate, 6.4 atmospheres. Does everybody see that? The logic there? Okay. All right. Well, let's kind of stick it down here in the corner. Yeah, just so it doesn't get in the way. All right, let's get back to business. So I don't want to eat up our lab time. Lab's more fun anyway. Okay, let's see. This is an interesting problem. Body temperature is 309 degrees Kelvin, which is what? Let's see if that's true. 37C is normal body temperature, 98.6. Close. Yeah, it's close. So we have to take their word for it. 309K. On a cold day, what volume of air at 276 must a person with a lung capacity of 2.2 liters to fill the lungs? All right, so if we're gonna start off with this temperature and we end up at that temperature, that's what I'm saying. We're filling the lungs. That's the final. That's where the air is headed. So that's the final temperature. Is 309. The initial temperature is 276 K. And the question, notice the question is, what volume of air at this temperature must be taken in to fill a lung capacity of 2.2 liters? So actually, it's not as complicated as it looks. We're looking for the volume here, right? How much of that volume needs to be taken in to fill lungs at this temperature of 2.2 liters? So now, when you look at it that way, it's just Charles' law. Right? If we solve for this one here, we'll just take this one and put it over there. So this becomes that. Then you can plug in your numbers. Temperature is already converted for you. So you just plug in this number here, right there, plug this number in here, plug that number in there, and you get the volume, the initial volume, which is at that temperature. And it should be 1.97 liters. Does that make sense? That's the next thing. Does it make sense? Well, if the temperature is lower outside the body than inside the body, the volume should be less. So yeah, it does make sense. Right? It's either this one or that one. And do the calculations and you find it's that. Okay, let's see if we can find something. We're not moving along too well here, are we? Where's my copy? Here we go. I want to be sure I get to a couple of these in here because they're really important concepts. I'm going to go down to 56. We can come back to some others, but I definitely want to get these that I've marked. And more. Let's see if I can do it without having to go over and scroll. Oh, I have to scroll. There we go. Okay. Which of the following, and these are graphs having to do with gases, best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and pressure. So volume and pressure are constant. That's important. So that means that what other variables do we have? Temperature and moles, correct? Oh, temperature, excuse me. No, I'm sorry. Temperature and volume, constant. These two vary. Okay. Which of the following is best qualitative graph of pressure versus molar mass? So pressure versus molar mass would look like what? By the way, which would we consider as the independent variable? Which one goes down here? I would think the molar mass would. Right? And that effect on pressure. That might be important, that's significant to put them that way. Okay, and you have 1 gram sample of different gas at constant volume temperature. Okay, so what we're saying is, as the size, the mass of the sample increases. No, it's a 1 gram sample, that's constant also. So mass equals 1 gram. Okay, did I lose anybody here? The size of the sample is the same. The variable is the molecular weight. So we're going to increase the molar mass of the gas. And it's 1 gram. So look at it this way. How do we determine molar mass? Right? Molar mass, I write molecular weight, is mass per unit mole, correct? Okay. So if this is constant, then we can put this over here equals our constant. That's constant. So now, if the molecular weight goes up, the moles goes down, right? So if the molecular weight goes up, the moles go down. And what relationship is moles to pressure? Look at it this way. PV equals NT is a constant, your combined gas law. They're directly related. If pressure goes up, moles has to go up. If pressure goes down, moles has to go down. So the variable here is molecular weight against moles. So what we're saying is the relationship here, this is, let's see, this is proportional to pressure. The number of moles is proportional to pressure. Right, with these things being constant. So if we substitute here a proportionality of pressure, then the relationship is inverse to pressure. So the best one here is a negative slope, right? As the molecular weight goes up, the moles and the pressure both go down. It may not be a straight line, but this is a qualitative graph. Did I lose anybody? Probably.
So the only reason D is not correct is the fact that it's not, it doesn't start at the axis there, the y-axis.
The reason that what isn't?
D isn't correct. And then it's E is the answer at the top, I think.
Oh, okay. Oh, good. That didn't end up being Q. It's freaked me out. Okay, the reason that this is not right is that it's a straight line. The slope is correct. It's a negative, it's an inverse proportion. But remember, pressure times volume equals a constant Boyle's law. It would be like that. Okay, that's why the straight line, I mean, we're close with a negative slope, but it's not linear. Like that. Okay. See if this one works a little better. Okay. Yeah, I like to look at these that have graphs with them because they always give students trouble for some reason, interpreting graphs. I don't know if you guys are in the same boat, but it just, all right, here's one with a picture. I think this one would be worth looking at. Number 94. 94. Go down some more. Oh, I skipped one. I think. Yeah, I wanted to look at 80. We'll come back to 84. 80. I will look at 94 first. Oops. Not if we go too fast. Here we go. Scroll. Yeah, that's got everything. Okay. So here's the scenario. This is, and based upon this picture, we've got two bulbs here attached with a valve. That's what that X means. And this one is a 3-liter volume, and this one's a 2-liter volume. So in the 2-liter bulb volume has a gas that's a pressure of 1.8 atmospheres. Let's just write it in here, 1.8 atmospheres. Okay, and the 3-liter has a gas that's 3 atmospheres. Okay, so that's where we're starting. There are different pressures and different volumes. So what's going to happen when you open the valve? Right, they will equilibrate. They'll become some middle point in there. Which direction are they going? They're going to flow from this way to that way, right? Yeah. High pressure flows to low pressure. Okay, so with the question of what's the final pressure in the two bulbs if the temperature remains constant? Okay, how do we answer this one? Well, we know qualitatively that the value is going to be somewhere between 3 and 1.8. We just don't know what it is yet. So how do we approach this problem? We approach the problem in 2 steps. First, treat it as if this one is a vacuum. And that finds out the partial pressure of this gas after. See where I'm going with this? Dalton. Then you treat this one as it's the vacuum and let that one expand into that space. That's the partial pressure of this gas. Now the total, according to Dalton, is the summation of those 2 partial pressures. Did I lose anybody? Okay. So if this is a vacuum, then what do we have? Pressure, volume, correct? So initial pressure times initial volume equals final pressure times final volume. So what's the initial pressure? If we let this be the vacuum, the initial pressure is 3, right? The initial volume is also 3. What's the final volume? 5. 3 plus 2. The final volume is 5. Now we can solve for this unknown. So this would be what? 9 divided by 5, 9/5. So this is the 3 atmosphere gas is 9/5 atmosphere. Okay? Did I do that right? The initial pressure is over here. We haven't opened the valve yet. initial volume is 3. The final pressure, the final volume. I did that wrong, didn't I? That's why you had a frown on your face.
Well, better I say, but yes, that's what it was.
So this is, final volume is 5 liters. There we go. So now, it's still 9 divided by 5. Okay, and this is atmospheres. Okay, how about the 2-liter gas? Okay, now in this case, we're going to say the initial pressure is 1.8 atmospheres, and the initial volume is 2. There's the pressure, and the final volume is also 5. Again. So this is, what's 2 times, let's see, 3.6. 3.6 divided by 5 is the 2-liter gas pressure, final pressure. And then the total should be that value. So this is 12.6 divided by 5. Let's see, can I do that in my head? 2.5, 210, 5, and then something like that. Atmospheres. Oh, there it is right there. Okay. So we used both Boyle and Dalton to solve that problem. Now let me go back up to 80. Oops. There we go. Go back up to 80. Oops, too far. Or is it 84? 80. This is going to take a little bit of algebra. There we go. If M is molar mass, okay, so I can't use MW, molecular weight. You have to say big M for molar mass. R is the gas constant, T is temperature, P is pressure. Which of the following expressions represents the density of a gas? So this looks like a big problem, but it's really algebra. So what do we know? Well, we know this is a state function. This is what it is right now, which means we use the ideal gas equation. That's first. So we need PV equals nRT. And I need another marker. There. Okay, what else do we know? Which of the following expressions represents the density of the gas? Well, another clue is they're giving us molar mass. So let's say, what do we know about molar mass? Molar mass is the mass of the gas divided by the moles, correct? Okay. We also know that density is involved. Well, actually, that's the question. What's the density of the gas? So density is equal to mass per volume. Okay. We need to combine these in some way so that the answer is density. There. Okay. What do we know? Well, let's see. We can approach this several different ways. What if we say this one is solve it for n because n is right here. There are no other common values in here to that expression, so we have to solve for n to put these two together. So n equals mass divided by molar mass. Right. So now if we plug that in here, that's PV equals mass divided by molar mass times RT. Okay. Now, what about density? We need to get density in there somehow. But we don't want to put this over there because then this would disappear. We want to put this over here somehow. So there's the mass and there's the volume. So what if we get mass divided by volume out of this? If we keep the mass here and put the volume over here, correct? It's still on the bottom. These are still on the top. That's on the top. And this one comes over here like that. Okay. Now we've got this term right here. So we can hold that one here and put these over there. So this one comes up here, pressure times molar mass divided by RT equals M divided by V, which is equal to density. Right? So pressure times molar mass divided by RT. Pressure times molar mass divided by, there it is. So that way, if we know these values, then we can calculate the density of the gas. Okay. Unless you're actually active in that industry, in gas industry, the only value for knowing that is maybe to impress your friends at parties. Okay. So I also wanted to get in here and solve a stoichiometry problem involving gases. I definitely want to do one of those. So let me see. How about 88? Yeah, okay, we can still see all the answers. Okay. 88. Oxygen gas is generated by this reaction. Potassium chlorate decomposes to potassium chloride and oxygen gas. I think we did one of these in lecture, similar to this. So use the same reaction. But this time we're going to collect that oxygen gas over water. So how does that work? I didn't show you this earlier in the lecture. So if you have the reaction in here, you got the potassium chlorate, right? And it's going to, you're going to heat it. That's how you make it decompose. And it gives off oxygen, right? O2. Well, we want to collect that oxygen and determine what volume is produced. So you do it like this. And this is underwater. And initially, it's filled up here with water. It's just inverted here. So as the water comes in, the oxygen comes in, it bubbles up here, and it displaces it. And we've got markings here so we can tell the volume. Okay. So we can tell the volume of what? You can tell the volume of oxygen plus water vapor. Okay. So you don't know the amount of oxygen yet. You know oxygen and water vapor. Okay. So what's the question here? How many moles of KClO3 were consumed in the reaction? So we want to know moles of that, right? We got the stoichiometry. We just need to know how many moles of oxygen are in here. Okay? Well, we can use Dalton's law of partial pressure. If we can find out how much water vapor is in there, subtract it from the total, then we can find out what the pressure of oxygen is. We need to know the temperature. The vapor pressure of water is very well defined at different temperatures. So that's why this bit of information here is given. Vapor pressure of water at 27 degrees is 26 torr. So at 27 degrees, pressure of water equals 26 torr. What's a torr? A torr is a millimeter of mercury. That's it. It's just, I guess they wanted to honor Torricelli. So 1 Torricelli is 1 millimeter of mercury. All right. So what's the total pressure at this temperature? 1 atmosphere. Okay. So that's 760 millimeters minus 26 is equal to what? 4 and 2 from 4, 2 from 5 is 3. 734 millimeters of mercury. That's the actual pressure of oxygen in that container. Right? Okay. Now we know, do we have enough information to solve this problem? What are we going for? We're trying to find out this, right? So that we can use stoichiometry and find out that. Get that cursor out of the way. Right. Okay, so we're going to take this knowledge. We know that the pressure equals 734 millimeters of mercury. What else do we know? We know the temperature, 27 degrees. All right. Let's see. Volume. Is 1.55 liters. That's this volume up here. 1.55 liters. Okay. And we want to find out moles, correct? So pressure times volume equals moles times the universal gas constant, ideal gas constant times temperature. I think we have enough information, don't we? We just need to find atmospheres here. 6 will be atmospheres. Why do we need to do that? Because of this. 0.08206 liter atmospheres per mole K. That dictates your units of measure. We have to convert this to atmospheres. We have to convert this to K. And liters are good. So once we find this value, that value, that value, and we know this one, then we can solve for that. Okay? Once you know the number of moles of this one, moles of oxygen, how do you get moles of KCl? Use the stoichiometry, 3 to 2. So 3 for oxygen, 2 for KClO3, and that's your answer. Okay? And it should be 0.0405 moles. You know, it may have been more instructive actually to solve this problem backwards. Right? The question is, how many moles of this? Well, the information that we have doesn't tell us that, but it does give us a handle on this. So then you work your way back through that. How do I find the moles of this? What do I know? Well, let's see. Volume, temperature. Yeah. Maybe pressure. So I could use the ideal gas equation. Then I say, okay, but we're collecting this stuff over water. So there's a fly in the ointment. How do I figure out that? And then you think Dalton. Dalton tells you how much oxygen pressure there is in there if you subtract out water vapor. Okay, let me see if I skipped anything that might be useful. We'll backtrack a little bit. Let me see. Is that a valid process? Let me see. Let me look further down the line to be sure I'm not. Oh, we haven't talked about Graham's law yet, have we? Let's see if I can find one of those that would be useful. All right. 103, this is a very simple one, but it's like it's getting us to that point. We want to start simple and get complicated. 103, calculate the root mean square velocity of oxygen molecules in a sample of oxygen gas at 11.8 degrees Celsius. Okay. So what are we looking at here? 103. Find a good bar. Another one in my pocket, I hope. Yeah. So we're looking for the root mean square velocity. And what is that? Well, I give it to you. I give you the formula you need right here in useful information. There it is. The root mean square velocity. 3RT over M. Okay. And they use a mu here, root mean square velocity. Okay, so really, it's pretty simple calculation. You have the R, which is you have to use this R because it's got the energy term in it, and then you need to know the temperature in K. So 11.8 plus 273. And 0.15. Right. So this one goes right here. This one is 8.3145. And this one is what? What's the molar mass of oxygen? Well, it's 32 grams per mole. But this one has buried within it kilograms because of the energy, kilogram meter squared per second squared. So this has to be converted to kilograms. So how do you make kilograms out of gram? Well, what's the relationship? A gram is 1,000th of a kilogram. So we need 32 times 10 to the minus third kilograms per mole, or 3.2 times 10 to the minus 2. And that goes in here. Now it's just crunching numbers, right? And it should come out to 471 meters per second. Okay. How are we doing on time? We got about 12 minutes left. Okay. Let's see. Actually, there should be a more interesting one. Okay, I might come back to that. 128, 129. But I want to see if we've got another opportunity here. Okay. Okay, how about 144? There. A gas is found to diffuse at half the rate of methane. Which of the following could be that gas? All right, what's the ratio? What's the relationship here? The rate that a gas diffuses is inversely proportional to the square of its molar mass. So what I'm saying is half the rate of methane. So we can not only say if the methane diffuses at this rate, right, then there's a gas that diffuses, our unknown gas diffuses at half that rate, right? Which means that not just, well, yeah, we can ratio those. So if we ratio this one to this one, let's see, no, that's not right. Excuse me. This one is equal to, let's put it on the bottom. First, let's do it this way. Okay, that diffusion rate is proportional to the molar mass of the CH4 and molar mass of X. That's true. Right? They're inversely related to the square root. Now let's substitute. What is this equal to? This is equal to VCH4 over 2. Right? So now that's equal to 2. So square both sides, right? Square both sides. Now you've got this one divided by this one equals 4. Okay? So what would the molar mass of this one be? It would be the molar mass of this one times 4. Right, so what's the molar mass of methane? Let's see, 12.01 and then 4.04 for the hydrogens. 1605 times 4. That would be the molar mass of X, the unknown. Let's see, 2, 24 to 64, right? Did I do that right? Yep, 64. So which one of these is 64? Well, that's not it. That's 32. That's not it. That's 28. 14 times 2. How about carbon dioxide? 12 plus 32. That's 44. That's not it. How about sulfur times 2 oxygens? 32 with sulfur. 3206. That's 64. That's it. Sulfur. Sulfur dioxide. Sulfur dioxide. Okay. That should be in useful information. Let me see if that particular form of the equation is there. Should be. Yep. It's given as ER, diffusion rate, in the lower right-hand corner That's the equation that I used. Okay? I said velocity here, but it's really diffusion rate. All right, we got time for one more. Uh, 128, back it up. We could do 128 or 129 or 130. Let's do 128. Okay. So a room is 16 feet by 12 feet by 12 feet. Would air enter or leave the room if the temperature changed from 27 degrees to -3 degrees while the pressure remained constant? And then determine the volume of the air that moved in or out of the room. All right, this is two steps, a qualitative and a quantitative. On my nerves. Mark it here. Yes. Okay. $128. All right. So what do we? The first step is the air going to move into or out of the room? If the temperature in the room suddenly drops from 27 to -3 degrees, what is that going to do to the volume of air in the room? It's going to try to decrease it, correct? So that means a decrease in pressure. So the pressure differential is going to move the air into the room. So that's the first answer. Air moves into the room. Now we want to find out how much moves into the room. First, we need to know the volume of the room. So 16 times 12 times 12. I'll actually do some calculations on this one. I know 12 times 12 is what? 144, correct? 12 squared. And then 16 times that. So that's 2.304, 2.304 times 10 to the third cubic feet. That's the volume of the room. Okay. And this is at the volume of air in the room at this temperature, 27 degrees. Okay. What would the volume of the air be if we decrease the temperature from 27 to -3? That's the key to this problem, because if you just allow this to decrease under constant pressure, we know that Charles' law will tell us what the new volume would be. But we know that it's not going to just decrease in volume and leave a vacuum over here. It's going to get filled, right? So we want to know what that fill is. Well, what's the new volume here? This is the initial volume. Final volume, that's the question. And the initial temperature, the initial temperature is 27 plus 273, which is what? 300, right? 300K. Yeah, 300K. And the final temperature is -3. It's 270K, correct? So this value here is going to be let's see, it's V over T. That leaves V here. So now we have T final, volume initial, and T initial. Right? V over I, V over I, V over T, V over T. So T comes over here. Okay. So this 270 times the initial volume, which is 2.304. See, I'm squeezing off to the right here. Do this. Pick up the rest of it. 04 times 10 to the third cubic feet divided by the initial temperature, which is 300. Okay, so this is the final volume. If the roof of the room would decrease and not let any more air in. So I'm going to multiply that times 270 divided by 300. So 2.074. 2.074 times 10 to the third. So what's the difference? Well, it decreased this much volume, so the air that moves in is going to be the difference between the initial and the final. So that's 2.304 exponent 3 subtracted. So I get 230 cubic feet, roughly. I get 226 this way, so there must have been some rounding error. Close. Well, I'll tell you what, this is two significant figures. So we're limited there. So that's probably the difference. 226, that's actually should be rounded off to 230. Okay, out of time. Anybody have any observations or questions that we need to deal with before we go in the lab, either about the this material or the lab material?